So again, you'll go to the package website, go to materials, and then go to the link for the code for fitting hidden Markov models. And if you open that up, I have some notes up here at the top that were originally for me, but might be useful for you as well. And then a lot of these packages we're loading are going to be the same. I'm actually going to reset or restart my R environments. So in this case, I'm loading in momentum, package version 1.5.4. I think there might be a more recent version, but this is what I'm using here. And I'm also loading in this other package I haven't shown before called R-erdap extracto. And this is made available by some folks at NOAA, where you can essentially use some R code to access the erdap repository for different satellite remote sensing data sets. They're available as rasters, and use that to download daily, monthly, weekly, whatever your data set is for all that they have available online. So that is something that I'm including in here, but I think it took you like 10-ish minutes to download all of the I think it was sea surface temperature data I'm trying to get. So I'm just going to instead load in that R object, so we don't need to sit around and wait for that to finish running. But otherwise, load in these packages. And hopefully for those of you that had issues with foie gras, this doesn't need the other steps and things to get going. So hopefully, assuming you're able to get that email from me with the more recent process data sets resulting from that state space model code, we can get started and hopefully you won't have any issues. So essentially we're reading in that data set that we exported at the end of the last session on state space modeling. That was called SSM MP 8-hour FDNC MIDAS tracks. And that's going to be our new object. I'm calling DAT again. And as always, just to refamiliarize yourself with what's there, we have 11 columns of about 2,200 observations. So we have the ID, date, lon, and lat. The X and Y are the coordinates in kilometers from a world Mercator projection, the standard errors on those location estimates, and then our behavioral state estimates, G. Okay, so moving on down. Again, we need to convert our date column to a date time format. So all we're going to do is run that as date time function from lubridates. And to get things working properly with the momentum package, we actually need to change the name of our ID column from lowercase to uppercase. Otherwise, it's not going to work. So for lines 35 through 37, if we run that, that's going to get our data frame in a state that we need it to be in. And then if we use this prep data function from momentum, we provided that data frame DATs, and then we define here the type. So whether it's in, I think the options are either LL for latitude, longitude, or UTM, which is what a lot of terrestrial studies use for coordinate reference systems, universal transverse Mercator. In this case, we're using world Mercator, but it essentially does the same thing, assumes it's in like meters or kilometers as units, not decimal degrees. And then we tell it in this argument coord names what the names of our coordinates are that we wanted to evaluate. So instead of lon and lat, I'm going to use the world Mercator values in kilometers because we want to use kilometers or meters to measure step lengths and turning angles. We provide that here. So I'm going to use that function, and then we can use that. I use a plot function to actually show these tracks with the dat2 object. So if I start plotting these now it'll show me a different plot per individual here, as well as the time series and the distribution for each individual for step length and turning angle. So if I zoom into this one, step length is shown here in the top left. So it's relatively small until we hit the middle of this time series where it's migrating, and then it decreases, but it tends to be higher here afterwards once it reaches that foraging area. And in general, turning angles are often really messy because they switch back and forth between like pi and negative pi a lot. So it's hard to tell what's happening. One way you could potentially modify this if you wanted to is just take the absolute value of turning angles. And then anything close to 0 means it's going straight. Anything going close to pi means it's turning around. But often we're not trying to discriminate whether it's turning left or right, or it's like a negative or positive value. So if you wanted to, you could just like after the fact, take the absolute value of this, and that might help clean up the visualization and interpretation. But we do see this short brief period here in the middle where it's close to 0, indicative of that migratory phase. Step length distribution is highly right skewed. It's almost all in this first bin of this histogram. Turning angles, there's a slight peak here in the middle near 0, but otherwise everything else is near negative pi and pi. All right, and then we'll get the same thing as we look at these other individuals, and we'll see that they're all relatively similar in their time series and the distributions, these histograms, with the exception of the resident individuals, where we see kind of like a larger peak here on the left for step lengths, and then the distribution for turning angles is a bit flatter with no real peak here at 0 radians. So that's one way to kind of initially inspect your tracks when loading these in. And we can also just plot these histograms or time series ourselves. So this is a histogram of step lengths. And this is showing the time series of step lengths. So again, you can just do this on your own in ggplot if you wanted to, but it's nice to have this convenient plot function when just getting that data set. And one thing that might be useful to use these for as well is you often need to define initial values that define the distributions for step lengths and turning angles or any other movement variable you want to use. So often it helps to look at a distribution like that or a time series like this and say, okay, let's say we want to identify 2 states, one where it's not moving much and one where it's moving a lot or really quickly. So maybe something close to 1 kilometer, in this case, since it's near 0, would represent that like ARS behavior, whereas maybe something that's 30 kilometers, since that's around the peak of where these spikes are occurring, would represent like our transit or migratory behavior. And then you also typically need to define the standard deviation. So usually some value, maybe half the size of your mean in this case might work. So I'm labeling those what I might use here in the comments underneath this plot. And we can do the same thing for turning angles. So this is our overall turning angle distribution. We have a peak here in the middle at 0, and then we have peaks on the edges at negative pi and positive pi. And then here are our time series. And it's a little bit easier in general, I think, to work with turning angles because especially if there's 2 states, okay, let's assume there's one peak or one state that's peaking at 0 and the other state peaks at negative pi and positive pi. So you would say maybe that the mean would be at 0 for this one state and then negative pi or positive pi for the other. And you also, depending on which distribution you're going to use to characterize this turning angle, you might have like a concentration parameter that ranges between 0 and 1. And I'm kind of defining what I'm going to be using here in this comment again. So this next part, extracting sea surface temperature. So this is the link that would bring you to the web page for ERDAP, where you can look into this variable. So if I hit Command or Control and then click on this link, it'll bring me to the web page. So we see this is the multi-scale ultra high resolution sea surface temperature data sets at 0.01 degrees or about 1 kilometer resolution. So for a marine data set, this is actually really high, especially like a global data set, and has data from 2002 to present on a daily scale. You can also get this monthly or weekly. And you can kind of explore it a bit here and see what variables are included if you wanted to explore this a bit more. But this is how I would access essentially this data set. And I'm going to do so directly through R instead of that website. So ways you would go about preparing to extract that sea surface temperature data is basically defining the, in this case, the coordinates of of these tracks if you want to get the value from each point in your track. Alternatively, you can download an extent. It's like a raster layer of these values. In this case, I'm just showing how to do it where you're extracting the value per point, per observation. So I'm calling these different, or defining these different objects. So X pause is the X positions for this DAT2 data frame across all individuals. Y pause is the latitude across all tracks. And T pause is the date for all these tracks, date and time. And we need to give it this label, so this code to define what exact data set we are downloading. So if I go back to the website, you see I'm using JPL MUR SST41. You can find that code here where it says data set ID, and each different data set will have a different unique code. So for a daily data set, this is the code, and you'll see a slightly different one for like a monthly data set. So you need to supply that using this RERDAP info function. And then you would run this function called rextracto and provide the objects, the parameters I just defined, maybe how much you're going to expand this bounding box. You can say whether you want a progress bar to be shown while it's running. You need to say which parameter. So in this case, I'm using analyzed SST or analyzed sea surface temp. You would need to pick a variable from this list here of these grid variables. Okay, so based on me timing this previously when I ran it, it took 11 minutes. So I'm not going to run it right now because that would waste a bunch of time. But this is something you could do on your own if you wanted to, and then repurpose for your own needs later on at some point. So essentially, I'm going to be skipping this piece of it, but I think now I need to reload in that DAT2 object because I, overwrote it. So let me get that back. But if I open DAT2 now and go to the end, so the third to last column here is sea surface temp, or SST is how I've labeled it. So this is our extracted sea surface temperature values that match up for each day. So these are time matched values. And I will close this now. So that's what I did there. And I'm also defining the day of the year, Y day, using this Y day function from Lubridates. And I'm also using the hour function from Lubridate to define the hour as a separate variable. And this is to potentially include these as covariates within the hidden Markov model. So look at these cyclical potentially patterns that are impacting behavioral transitions. And because just knowing relationships between the day of the year and sea surface temperature, you'd assume it's colder when it's winter versus summer. Let's see if there's any correlation that would impact basically like collinearity that's impacting or present in this data set. And if I was to plot these two things, we can see that sea surface temperature increases and then peaks and then drops off again after like March, April. So we don't have any data in this region from day 200 to 3 something, which is kind of summer-ish. But we can see that there is some kind of cyclical pattern presence that would potentially confound our interpretation of what's happening. So I'm essentially not going to be using the year day. I'm going to stick with potentially investigating the hour, since a lot of these observations were originally at a hourly scale. So we've predicted them at an 8-hour time scale, but we'll still have maybe some patterns that are present here based on the time of day. So now we get to the point that's, in a sense, really subjective, where you need to potentially play with different values to define the initial distributions for each behavioral state. And these are kind of finicky in the sense that you need to put these in a very particular format to get this to work. Otherwise, it's just going to kind of crash on you and fail on you. So we have these different variables I'm calling step par 0 and angle par 0. These are our initial parameters for step lengths and turning angles for each behavioral state. So the first hidden Markov model I'm going to fit is going to be a two-state model. And I'm only going to be analyzing step lengths and turning angles, which were calculated by that prep data function that we ran early on. And then based on those time series plots of step lengths and turning angles is how I decided what values to put here for the means. So a mean of 1 kilometer and a mean of 30 kilometers per step for state 1 and state 2. And then after that, we provide the standard deviation for state 1 and state 2 that we think is present. So this is subject to change, but this is like where the model will start from. Similarly, for turning angles, let's say they both start at 0 radians or 0 degrees, but that our concentration parameter is going to be 0.2, meaning that it's relatively flat for state 1 that moves relatively slowly. And then it's going to be close to 1 for state 2, which is moving in a directed fashion. One thing to be careful of is sometimes these distributions won't particularly work if you use like the last value of that range. So in this case, I don't think it's possible to use a concentration value of 1. Otherwise, the model will tell you it doesn't work. So it works up to 1, but not equal to 1. Same with 0. Like it won't work if it's equal to 0, but if it's close to 0 and it's just really small, it'll work fine. And there's more info on how to properly set these on the guideline, the guiding PDF for this package. And that's linked to on the workshop website. So I'm going to run these lines to define our initial parameters. And then one thing you should typically always do when you're running some type of model is to set the random seed if you've never done that before. So I'm using set.seed, and this could be any number. This could be 1, 2, 3, 2022, 1990, whatever you want to use, some huge number. But this makes sure that your results are reproducible. So anything that has some stochastic underlying process, like a hidden Markov model or a state space model, you'll get probably different results, slightly different results each time. So to make sure that somebody else can reproduce your results or you can reproduce your own results, you want to make sure that it's the same result every time. So in this case, I'm using a value of 1, 2, 3 for my seed. And then I'm going to run the code here, this function fit HMM, and I'm assigning it to object fit HMM 2 states. So first we supply it the data, and this is our dat2 object. We tell it the number of states, in this case is 2. We also want to define the types of the distributions we're using, and this needs to be supplied as a list. So I'm saying this list where the step length, step, which is the name of our variable in our data set dat2, is equal to this character string gamma. So I'm using a gamma distribution to model step lengths. And for angle, which is our turning angles, I'm going to use a wrapped Cauchy, which is abbreviated WRP Cauchy. So you would need to look at the help documentation for this package to look at how other names are potentially abbreviated for other distributions. Then for par 0, par not, these are our initial parameters for step lengths and distributions that we just defined here above for each state. Formula, this is where you would put in a formula on the, basically if you were to include covariates, so looking at the impacts on behavioral state transitions due to, in this case, we're going to be looking at sea surface temperature. Estimate the angle mean, I forget exactly why I set this, but I'm leaving this where angle is equal to true. Then we're going to also, in this case, supply the name. So what we think these behaviors are going to represent, these behavioral states. I'm calling these encamped and migratory. And then I'm using this argument here at the end called retry fits. And that is to ensure that we're going to find this global maximum likelihood. So maximum likelihood estimation can sometimes get stuck in a local maximum, but it might not mean it's the global maximum if it was to explore like a larger range of different parameter values. So to try to make sure that we find the best fitting model, we want to try to run this different times with different starting values. So I would generally recommend fitting this with 30. But for the sake of time, because otherwise for some of these larger models, it would just take too long to run them. I'm just using 10 just to show you. So in this case, this basic model should only take about 30 seconds. So again, using this TikTok function or package, and it'll give you this printout. So fitting HMM with 2 states and 2 data streams shows you how you defined your step lengths and turning angles, and to see if there's any covariates on these parameters or on your transition probability matrix or your initial distribution. We see here that the number of attempts, so the number of different iterations of fitting random perturbations to these parameters. And once it hits 10, it'll finish. Okay, about 30 seconds. Now it's done. So now we can start looking at the results. So first, just printing this model fits. We get some readings back. So if I scroll to the top, it gives us the value of our maximum log likelihood, which in our case doesn't really mean much until we start comparing models using information criteria like AIC, BIC, things like that. But the stuff beneath it is what's more informative in general for inspecting the model. So for the step length parameters, for our encamped states and migratory states, we have the mean value on this top row and then the standard deviation on the bottom row. So the model in this case is estimating the encamped mean step length is just less than 1, while for migratory, it's about 13. So initially I specified the mean might be around 1 for encamped and 30 for migratory. But in this case, the hidden Markov model is saying it's actually 13 probably, with a standard deviation about 13 as well. So sometimes it's close to your initial value, sometimes it might be far off. And you can always rerun the model again and use these values in place of it to see if that might help improve your model fit. For turning angles, our encamped state says that the mean turning angle is close to pi. So that's good. That's representative of what I initially thought. And the concentration is relatively low at 0.4, whereas the migratory mean turning angle is close to 0, and the concentration is about double that at about 0.7. So far, so good. Then we look at these transition probabilities. So this is the intercept if we were to have, again, a linear model on these transitions, but what's kind of more telling, at least for this model, is this matrix. So the probability of being in encamped and staying in encamped is almost 100, it's 0.99. While for being in migratory and staying in migratory is 0.92. So essentially, if you're in a single state, you're probably going to stay in that state for a while. And then on the off diagonal is the probability of switching from one state to another. And we see that those are also relatively small. In our initial state distribution here, so delta is 1 for encamped, meaning that it assumes that initially everything is in this encamped state, and there's almost no probability of being in the migratory state to start off. If we use the plot function on this fitted model, we can also start seeing some nice outputs to look at these results. So initially here, we have our step length distributions. So on the x-axis, the label is step, and then we have our probability density on the y-axis. So you'll see in gold here, or orange, the encamped states is a really high probability of exhibiting these really small step lengths. And again, these are in kilometers. Over 8-hour time periods is the data set we're using. Whereas for migratory, this distribution is really kind of flat in this sense, meaning that it's got a really long tail off to the right. So it can include some really long or high step lengths here. Okay, next is the turning angles. And we see that for encamped, there's this peak. Essentially, it's a single peak if you were to wrap this around on itself at 180 degrees or negative pi, positive pi. And then for migratory, we see a smaller peak, but one that's present at 0, essentially meaning that it's going straight during that migratory behavior. And this is all matching up with intuition of what we essentially would have expected to find. So that's always promising. It's kind of emphasizing what we initially thought. And then we see these maps essentially showing the tracks themselves and then have them annotated with the behavioral states. So again, this gold color, orange color is the encamped states, and then in blue is the migratory states. And at least at first glance, it appears to do a good job. Same for this second individual. And then we see for this individual that was resident that it's essentially entirely in camp. There's no migratory movement. Same for this individual, so that's good. And then this last one we see, again, a migratory phase and then 2 encamped phases with some mixing potentially here at this foraging ground of different states. So that's good. And next we want to look at some model diagnostics, potentially looking at like goodness of fit. And in this case, we're going to look at pseudo residuals for this hidden Markov model. And you can define as an argument n cores, like the number of different cores on your computer, to speed up this process of showing you these diagnostics. So I will show that really quickly. All right. So again, this is to interpret the goodness of fit of your model. Same with like running a linear regression and looking at QQ plots and looking for homogeneity of variance, all those kinds of things, normality. So one of the things you often would do is look at your plot of residuals. And essentially you don't want to see a pattern at all. In this case, for step lengths in this top row, there appears to be some kind of weird pattern showing up, and it's not really clear why. But based on these plots for the QQ plot here in the middle, and then this autocorrelation plot to the right, it seems that it's not the best fitting model. There's definitely some issues with it. Turning angles tend to be fit better in this case by the model, but something else is impacting these step lengths. So hopefully we'll end up finding a better model as we kind of run different versions of this. But you wouldn't want to keep these as like your final results because the goodness of fit here isn't great. So let's move on and run a 3-state model. So track this down. Let's say I want to see if there's a difference between this breeding sites, so where they're staying at initially at Fernando de Noronha, whether they're actually breeding or just hanging out there residents, versus their foraging ground when they move back to the mainland, and then also accounting for this migratory period. So we're going to take a look back at these time series plots to try to define our initial values again. So we're going to assume maybe that this period before the migration is one state, so basically like this breeding or encamped state. Then the migration period is another state, and then when it disperses and migrates from the breeding ground to the mainland and reaches the foraging ground, that's a different state because it appears that there's higher step lengths and more variability here. So some initial values that I might be considering here, I've included in the comments, where the means and the standard deviations are a little bit higher for this foraging behavior potentially compared to the encamped or breeding behavior. Same thing for turning angles, you can look into that. But in general, I'm going to assume that turning angles are going to be similar between the like breeding encamped state as well as the foraging state. They're probably doing the same type of turning, whereas the migration or migratory pattern or phase is particularly straight. So I'm defining these parameters here. So the first sets of values I need to provide, these first 3 values, are the means. So I'm calling these mu1, 2, and 3. So the mean step length for state 1 are the encamped or breeding states. The mean for state 2 or this foraging states, and the mean for step 3 are the migration or migratory states. as well as their standard deviations in order. And again, same for turning angles. So I'm going to assume, let's say they're all having averages at or means at 0, but the concentration parameter is different for each of these, where it goes from very flat to very peaked at 0. So I will run these lines again, set my random seed value here just above my code. And it's going to look almost identical to the previous version of the model code, except I'm setting number of states to 3. The distributions, initial parameters, lines are the same. The only other thing that's changing is the state names, where now we have breeding, foraging, and migratory. So again, I'm going to highlight all of these to time it, but based on my comments, this should take 2 minutes to run. And if I was to run this for 30 different retries or different fits, perturbations of the model, it would take even longer. But if you're actually doing this for an analysis for like a paper for your research, I would ultimately suggest that you do probably at least 30 fits, separate fits on your own. One thing that can be an issue I've experienced in the past is if you, let's say, run 30 like retry fits, but for some reason the model fails halfway through by like try 15, then you don't get anything. And you could have waited like half an hour for that. So one thing I would recommend is, if you do run into that issue, is essentially to write a for loop and to specify the perturbations yourself, where you're pulling these values, these initial values from like a random distribution. And then you have those fed into the model. And instead of saying retry fits equals 30, you can just leave there or ignore that arguments, because the default is 0, essentially. And you're just manually doing it yourself. But you would need to assign it to like a list where it puts in each of the results, and then you find which one has the maximum likelihood, and then you keep those results from that model fit. So that's kind of a special case if you run into issues during this process, but I think it is useful to know if you do plan on using hidden Markov models and then run into some of these technical issues. All right, it's on attempt 9 of 10, so it looks like it's almost done. Okay, so yeah, it took about 2 minutes. Now we can look at the results from this model. So scrolling up, again, we have our maximum likelihood estimates, but now looking at these step length parameters, we see that they're actually relatively close to what we guessed at initially. So the means for breeding is close to 0.5. For foraging, it's about 1.5, and migration or migratory is about 22. So these are actually pretty close to our initial values. Same goes for these standard deviations. So that seems to be working pretty well. The breeding and foraging turning angle averages for the means are both basically pi, close to pi. So it's turning around a lot, with concentration values almost equal to each other, about 0.4, which is what we got for that breeding states in the 2-state model. And then for the migratory states, the mean is close to 0, and the concentration is actually even closer to 1 at 0.87. And then now we have our 3x3 transition probability matrix, where initially you probably want to look at this primary diagonal, and it looks like they're all about 0.98, except for migratory, it's 0.93. So this means that what's the probability of being in a state and then staying in that state? And it's all high. If you see one that's really low, that might be indicative of a problem. Or if you see one that's exactly equal to 1, that might be an issue also with just how the model is fit. So it doesn't seem like it's likely to happen. And then everything off diagonal is what's the probability of being in a state and then changing to a different state. Okay, and then our initial distribution at the bottom, where there's a much greater chance of being in breeding, instead of foraging or migratory. And let me check the chat really quick. Breeding with mean 1.5 fish, foraging. Yeah, I would potentially change the random seed value or increase the number of retries. So I think when I was initially doing this Vic, I think my seed value I had set was 2022. Maybe I had the two-state model. And yeah, it was giving me problems with the states were being flipped. So that is one issue potentially with like this maximum likelihood approach is you get these weird things happening. So I would try some combination of or doing one or the other, changing the seed or just running more retries. Okay, so if we want to plot these results again, but for the three-state model, looking at this distribution of step lengths, again, in orange or gold is that breeding behavioral state for step lengths. So again, it's really small, but in blue now is our foraging states. And we see that it's also shifted towards the left here, that they're really small step lengths, but they have some larger step lengths than the breeding states. And then in migratory, it looks about the same as previously for the two-state model, where it's just really small and flat here, indicative of higher step lengths compared to these other states. Going to the next plot, turning angles. We see that the turning angle distributions are nearly identical for the breeding and foraging. They just differ slightly based on this density value. But that's not really going to impact the interpretation at all for the turning angles. But then again, migratory is nice and peaked at turning angles with 0 radians. So going straight. And now we can look at these plots of these behaviors in space. So we see again in orange or gold would be the breeding, blue is foraging, and green is migratory. And it's actually kind of hard to see the breeding state because it's kind of hidden underneath the foraging states, especially at least at the island Fernando de Noronha. And it's possible there's some even at the foraging location as well, depending on how the model identified these. Take a look at this next individual. And it's only really possible to see these two states. It's hard to see that breeding state in general, at least from looking at these results in this way. But for the resident individuals, it shows that it's entirely in this breeding state. But for this individual that was resident, it actually has a movement. It's labeling as foraging. And then there's no real way to be able to distinguish, I guess, in this case, what the difference would be apart from, again, the potentially longer step length. So we have this large spike outwards, and that's probably why it identified it as foraging. But in this case, that's kind of misrepresentative of what might be happening here.
Yeah, it seems that for those that migrated doesn't have the reason.
Yeah, it's partially probably like underneath other points that are labeled foraging, or the model just did a poor job of identifying them in this case based on how we set it up. And then we see this other individual where it identifies some foraging stopovers during this migratory period before it reaches its final foraging ground. But ultimately, the results you get are in large part due to what you feed into the model, whether that's the initial parameter values, the way you're characterizing or trying to define each behavioral state, the variables you choose, the time scale at which you're analyzing it. So there's all these different components that can feed into your ultimate results. So if you're not getting what you initially anticipated, one, that could just be the way the data are, and there might be something you overlooked, or two, you need to go about it a different way to kind of match up with what you are trying to find in this data set. So one other way to potentially explore the time series of these behaviors, if you can't see it that well on a map like this, is to use this plot states function on your fitted object. And this will show a difference. That's not great. Plot per individual. It's giving me issues. Let me see if I rearrange this, if it fixes it. Why is this happening? Try this one more time. There we go. All right, so for this first individual from this function, we see a time series of the different states it was in on the top row, and then the probabilities of being in each state and each subsequent row. So the probability being on the y-axis, time is on the x-axis. So we see in the very top, it's primarily in state 1, so that breeding state, and then it moves to state 2, so the foraging states, and then into state 3, the migration, back to state 2, foraging, back to state 1, breeding, and then ultimately in state 2, foraging. So this isn't really capturing what we initially were thinking, where there's a breeding phase before the migration, and then there's like a foraging phase afterwards. This is kind of mixing both of them before and afterwards, which is possible because obviously the resident individuals have to be feeding, but their movement patterns don't look the same, have as higher step lengths and greater variability in later phases after they're done breeding. So this model is not really capturing what we were hoping for. But let's look at these other individuals. So this next one starts in state 2. So it was never even in the breeding state to begin with, migrated, and then went back to state 2. So we see in general that if you look at the probability on the y-axis for state 1, it doesn't get above like 0.25. So it's always really low. Again, just emphasizing that this model does okay, but definitely has some issues. This is the one of the resident individuals, basically always staying in that resident or breeding states. This other one that had that spike as labeled as foraging, and then this other migratory individual where it's shifting a lot between state 1 and state 2, apart from the migratory phase. So just there's a lot of nuance in what we expected that's not being picked up in the way we coded this model and try to fit it. So now I'm going to rearrange the size of these windows again. Okay. And you can even look at the probability of being in one state or another for each time. So if you type in time and states, it'll give you the overall like probability of being in one state or another for the time series that you've analyzed. So about 60% of the time, these individuals are being evaluated as exhibiting breeding, whereas 37% of the time they're in foraging, and about 3% of the time they're in a migratory state. Again, we can look at these diagnostics, and it looks like the autocorrelation plot for step length is a little better. The QQ plot might be slightly better for step length, but the pseudo residuals plot is still kind of weird here, wonky in the middle. So that might not be really anything. It could just be some other aspect of the tracks, but it's something to consider as we move forward. But this is definitely a step up from that 2-state model that we just looked at. Okay, so moving again in a slightly different direction. This case is starting to include environmental covariates. So before it was just focusing on step lengths and turning angles. Now we want to look at the impact of, let's say, sea surface temperature and the cyclical pattern of the time of day or the hour on these transitions from one state to another. So we're going to define this formula using this formula syntax. So we have the tilde sign, and then sea surface temperature and its interaction, so the star or the asterisk, with this cosine r function, where we're feeding it in the hour variable. And then this is over a period of 24 hours in a day. So that's like the daily cycle that we want this to be evaluated over. And we're going to let the previous model fit from the two-state model help us define our initial parameter values here. So we're going to give it the model we fit previously, the two-state model, since we're fitting another two-state model here, as well as this formula. And this will give us initial values without needing to specify them ourselves, so save us a bit of time. And again, setting that random seed and running this code. And again, two states, but instead now for par not and beta not a new arguments. Par not, we're calling from that object that we just defined, par not covar. And then we're also supplying these estimates for the intercept slope values for this regression for these covariates. These are beta. We're also specifying our formula here that we defined. And then again, the number or the names of the behavioral states. And it's just coming up on 3 o'clock. So I'm going to try to run through the code a bit faster with a little bit less explanation. Or maybe I'll skip running some of the other later models and just look through the results in the sake of time. Okay, so look at the output from this. You would just print this out and you get those same values as before, except now we have regression coefficients for our formula we provided, but these are hard to interpret just looking at these values alone. So it's better to plot everything. For the plot function, we're going to supply these arguments, plot CI, so plot confidence intervals equals to true, and plot stationary state distributions, in this case, equal to true, to show the impacts of these covariates. Okay, so again, our step length distributions look the same as before. Nothing new there. Turning angles also look the same as before. So that's unchanged essentially. But now we get these new plots showing the impacts of the covariates on the transition probabilities. So we have these confidence intervals, in this case over sea surface temperature on the x-axis. And then this is essentially indicative or representative of that transition probability matrix. So the upper left quadrant is probability of going from state 1 to state 1. The bottom right is state 2 to state 2. The top right is state 1 to state 2. And then the bottom left is from state 2 to state 1. So if you're in state 1, you're probably not going to be leaving state 1 for the most part. And that doesn't matter whether your impact or what the value of sea surface temperature is. Same with changing from state 1 to state 2. It's just a low probability and there's not much real impact from sea surface temperature. Whereas if you look at changing from state 2 to state 1 or staying in state 2, there is a noticeable impact where at really low temperatures, based on what they've experienced in this case, there's a greater probability of being or transitioning from a migratory state back to a foraging or breeding state. And once they're in water, that's up to about 28 degrees, 28.5 degrees Celsius. They're essentially just going to be only in state 1. We're not changing essentially. Whereas the probability of staying in state 2, so staying in a migratory state, increases as the water gets warmer up to about 28.5 degrees. And then there's a almost guaranteed certainty of staying in a migratory state. So yeah, the probability of them switching is essentially 0. Okay. And that's also looking at using an average hour, so average hour of the day that we included before. And these plots may look different if you look at a different time of day, but this is looking at the average hour of the day. So the overall probabilities based on sea surface temperature alone show that the encamped state is most likely to occur at colder temperatures relatively. And then as you hit about 28.5 degrees is when there's this shift to be more likely in a migratory state by comparison. So this is some type of ecological inference that's actually really potentially insightful compared to what we had before, where you're only looking at step lengths and turning angles, but you don't know maybe the drivers of why they're going from a breeding or resident state to a migratory state. And now, instead of focusing on sea surface temperature, let's look at the effects of the hour of the day. So in general, there's not much here. I mean, it seems like it's kind of noisy, but there's nothing really interpretable. So for staying in state one or changing from state one to state two, there's a slight change around like 8 in the morning, roughly 9 in the morning. But it's not much of one. Whereas for state two, either changing to state one or staying in state two, it's also generally not changing that much. So it doesn't seem to be much of an impact visually here of time of day, but we can continue on to see what these results look like. So this is based on the average sea surface temperature, which in this case is 28.29 degrees Celsius. We see this shift over time where in general, they're more likely to be in an encamped state, essentially when it's dark out. And then there's a greater probability of being in a migratory state during the middle of the day, or at least mid to late morning. So obviously that's not always the case, but at least during the period maybe where they're actually migrating, it would make sense that they're like not really moving much at night necessarily, and maybe moving faster during the day. But it kind of remains to be seen if hour of the day is actually really useful here for us. And now we have our maps of these state estimates. And since it's only 2 states, we have an encamped state and then our migratory state. And in general, these look about the same as before. And then we have our other things you can look at for the time series, the stationary state distribution, the pseudoresiduals. But I'm going to skip those to continue on. So let's say you wanted to look at directly the impact of sea surface temperature on the mean step length or standard deviation of step length, or the mean of turning angle and the concentration for turning angles. You could do that as well using this design matrix, which I'm labeling DM, and compiling from this list of lists and doing something similar with this get par not function, calling in the model we just ran and fitted. So the fit HMM2 states Covar1, using the same formula as before, but then also including the effective sea surface temperature on these parameters. And you can run that, and I'm going to just look at the results, I think, if I have it loaded, so I don't have to and waste time. Yeah, so you can plot the results again from that fit. And now let's look at these plots to look at the impacts of the variables on the distributions themselves. So we can look at the effect of sea surface temperature here on the encamped state, the step length mean value. So the step length actually appears to decrease, the mean decreases with increasing temperatures. There's a negative relationship here. And then this is the standard deviation for step lengths for the encamped states. And we see that that slightly decreases, but doesn't change that much. Same for migratory. We have our step lengths over sea surface temperature. And we see that there's a much larger change here where step lengths for migratory states are much higher at colder temperatures. And then as it gets to warmer temperatures, they're much smaller. And then this looks very similar for our standard deviation for migratory. And we get our state-dependent distributions for step length and turning angle for each of the encamped and migratory states. And then here is the effect of sea surface temperature on turning angle. And it looks like it's really like a steep negative drop. But if you look at these values on the y-axis, it's basically all just negative pi. So if this was to be rescaled, it's completely flat. Same goes for this concentration parameter. It's really not changing much at all. And then for migratory, the same pattern, negative pi and flat for the concentration. So this is our distribution for the turning angles, where we have a peak at negative pi pi, and then it's relatively flat here actually. For migratory, there's not actually a peak at 0, surprisingly. And then again, the impact on the transition probabilities. So we see that there's just large error bars here, but showing a similar pattern as previously. And it's just kind of hard to make sense of this here. So it might not be the best fitting model of the bunch we've done so far. And then again, another plot for the hour of the day. And then again, showing how probabilities change over the course of an hour of a day overall for average sea surface temp. And our mapped plots. All right. So there's another model doing something similar for 3 states. And then a model comparison. So I'll just show you the model comparison so we can kind of speed this up here. But essentially, of all the different models that have been fitted, it's saying that this one with 3 states in the covariates turned out to be the best fitting model, supposedly based on AIC. And it's giving it essentially a weight of 1 so that everything else doesn't really matter too much. But doesn't necessarily mean it's the most interpretable for actually like understanding what's happening here. In the subsequent code that's in this script, I'm calculating the displacement, so the distance between the initial location and all other subsequent locations using this function I define here, calcdisp, to calculate the displacement and running it on each individual. And I'm essentially using some code here to define beforehand what I might consider breeding versus migratory versus foraging. And I just want to show you the results of running this. So this is a model that's using 3 behavioral states and 3 data streams. So step length, turning angles, and displacements. And we're just low on time, so I just want to skip ahead to these results because this is what I'm going to use to show later on during the method comparison at the end of today. But if I just plot these results, we see here 3 behavioral states. So again, breeding as the peak closest to 0, and slightly larger step lengths for foraging, and then the larger step lengths for migratory. So we saw that before with the 3-state model. The for turning angles, again, peaks around negative pi for breeding and foraging, and a peak at 0 for migratory. But now getting into the displacements, we have something different here, where there's a peak here for the breeding state, basically at 0, where it's like not moving at all. And then we have these larger long distributions for foraging and migratory. And that's because migratory can span the full length of that like migratory corridor, that migratory path. But then at different points along there, depending on how far away they move, some individuals might stop after 200 kilometers and that's their new foraging ground, whereas others might travel like 1,000 kilometers to reach their foraging ground. So these are both really diffuse distributions for foraging and migratory. And this is going to be really useful for distinguishing between something that's at the breeding ground versus at a foraging ground, at least away from this island. And now if we look at the plots, we see that this is identifying this breeding ground around the islands. We have this migratory period in the middle, and then once it's reached its terminus at the end at the mainland, it's identifying it only as foraging. It's not a mix of foraging and breeding. And it's not saying there's primarily foraging at this initial location. So same thing for this individual. It appears to be doing at least more of what I was trying to get the model to do, is to identify a breeding ground region set of movements versus migratory versus foraging that was a little more variable, but still similar to breeding. So we see for these individuals that never left Fernando de Noronha, they all are breeding. And then again, we have this migratory phase. This individual, it stops the mainland, enters this foraging activity, and then decides it wants to move south further, enters migration again, and then stops again into this foraging behavior. All right, so I fit another model after that to actually incorporate the sea surface temperature. We're not going to run it, but in general, I think the 3-state model here with nets or with displacement, but without the covariates, tends to do a better job. And ultimately, I'm exporting the results of that to look at further. So it is now 3:15. So we're just shifted back, let's say 15 minutes. So let's say we'll take the next 15 for taking a coffee break, and we'll pick back up at 3:30. And I'll try to get a little bit closer on schedule with the next topic with the Bayesian models.
Hey, Josh.
Yes.
I have a quick question, because you have turtles that are more like resident and the ones that migrated. Do you think the, threshold values that would define the behaviors could change if you analyzed the migratory turtles and the, residents separately? Like, would you identify different behaviors, you think?
It's definitely possible. So I think that's one of the benefits of analyzing multiple different types of tracks together, which is what we're showing here. But some of the things I included in the code that I didn't have time to discuss further was like how I wanted to visualize or think about kind of predefining these states. So if I looked at the time series of like step lengths and displacements, it's like, okay, anything that's moving at a step length greater than like 4 kilometers is probably going to be like in a foraging state, and anything less than that, where displacement is less than some value, means that they're not leaving the island and they're moving short distances.
Okay.
So it just requires a lot of data exploration and like looking at these different summaries. So either looking at the time series of different variables, looking at the histogram of them, and then kind of specifying a priori what you think is happening. And then hopefully the model will find something close to that. But yeah, there's no real way to know. This is a stochastic model that has a mind of its own in some cases. So like what Vic had happened to her before and what I've had happen to me in other instances, you could like define your different behaviors, and then the model will flip them on you and say like migratory has like the short step lengths and high turning angles, which is what you would have expected for like the breeding behavior. So it just needs like either a different random seed or more retries or something else to help constrain it. And I think there are arguments you can include in the function to fit the model that help constrain it to only certain range of values. But that's just more other stuff you would need to do upfront. But yeah, there's all these like things you need to do to tune the model to get it to work properly. And that's not even us trying to decide what's the optimal number of behavioral states. So let's say in this case, I think that there's 3 states. There's a breeding, migratory, and foraging states. There might be a 4th state that I don't even consider because it's just not something I've thought about, but it could exist. And I could be able to identify it with my data, but it's just, not something I know to look for. So that's like an added complication with doing this is a lot of times you're searching for something you think you already know the answer to. And in some cases that might be the case, or that might be true, but in other cases it's a little more exploratory, where if you have really like high resolution fine scale data, you might not know what you could even detect. There might be all these things that you didn't know were possible. and you would just need to run all these different possibilities based on different initial parameter values. And it's not ideal. You could do it, but it's just really difficult. So that is one thing that I think the next topic, looking at the non-parametric Bayesian modeling, does well, is it allows the model to estimate the number of behavior states, the likely number, simultaneously while estimating these state-dependent distributions. But again, yeah, there's these trade-offs based on what you're trying to accomplish.
It's exciting to see some of like the analysis and just think about what it's really saying and the potential of, looking at the behavior more closely. So no, it's cool to actually have the data from students, as well.
Yeah, so
are much excited and quick, like just looking at it, like just thinking about what we observe and the possibilities, I guess.
Yeah, there's a lot. I mean, especially once I get to the end of this, and then I'll compare the results of all three models. And in some cases, like they're really not that much different from each other. You're getting like the same results, which in some ways is reassuring that you are finding something that's detected across whatever method you use. But depending on how you want to get to that answer, if you're really interested in the effect of covariates, it's like, oh, okay, I know there's really an effect of sea surface temperature on the timing of these migrations, then maybe that's something that like really needs to be in your model. Whereas if you just care about where's the foraging grounds, or how are the migratory movements impacted by ocean advective currents or something, you might need to account for these impacts in a different way. But ultimately, it depends on the research questions and what you're trying to achieve, because with a data set that's transmitting hourly, there's a lot of possibilities. In this case, I'm coarsening the data essentially to 8-hour time intervals.
Okay.
So we're looking at these really broad time scales, whereas with the actual data set itself, if we left it at the raw time scale or regularized it to 1 hour, which is about the average time step, like I showed for the state-space modeling, it's really noisy. And that's probably because it's picking up these actual like dial patterns. But if you're not interested in dial patterns, that's just noise. You want to smooth that noise out. So that's why in this case, I'm using the 8-hour time step. But yeah, there's plenty of possibilities.
Cool. Thank you.
Yeah.